So let's go ahead and get started with today's lecture, right? Like I said, we're going to finish quantum mechanics and then jump right straight into my favorite stuff, which is chemistry. Do you think it'd be weird if I taught the lecture from back there? Okay. All right, I won't do that then. um, the Let me make sure my little clicker is connected. There we go. So let's just finish off quantum mechanics real quick. So this is the slide that you last saw on Wednesday, right? Uh, Schrodinger, the guy that came up with Schrodinger's cat, right? He uh, he came up with this equation that related energy, right, to a wave. Okay, that's all you need to remember about that. Okay, so here's the kinetic energy and the potential energy, right? And if you cut out the size, it just equals total energy, like you remember from the very beginning of the semester. So he put in there psi and showed that there was a relationship between energy and the wave, right? And it's proportional, okay? And the wave function is basically a mathematical formula that tells you what the shape of a wave looks like. I'm not going to ask you to do that on an exam or anything like that. I just want you to know that the wave function is proportional to the energy, okay? Because they're both on the top, right? There's no fractions there. Does that make sense? Right? So just to finish off stuff with quantum mechanics, Schrodinger's model focused on a wave nature of electrons and treats it as a standing wave in a circular orbit. The permissible orbits must have a circumference that will accommodate the whole number of electron wavelengths, and the circumference will not accommodate a whole number of I forgot this Greek letter again. Lambda, right? Thank you. Number of lambda. Then this orbit is not probable. Okay, so that's a lot of stuff that kind of doesn't make any sense, but it will make sense when I show you this picture right here. Okay, so this is say this for the electron wave to be stable, the circumference of the orbit must be a whole number of wavelengths, right? And so here is the circumference of the wavelength of an electron, n equals 4, and you see there's like 4 little humps there, right? And then here is one that's n equals 5, and you got 5 little humps here, and they're still all aligned, right? But when you get to a n equals 1/3, there's misalignment, right? There's no such thing as or not no such thing, but it can't be a complete stable orbit, right? So remember that the n equals the distance away from the nucleus, right? So n equals 1 was closest to the nucleus, n equals 2 was second closest to the nucleus, n equals 3, n equals 4, and so on. And the further away you get from the nucleus, the higher the n is, right? And Schrodinger figured out that these numbers, n equals 1, 2, 3, 4, and 5, and 6, and so on, had to be whole numbers. Because if you had an n that's equal to like 1/3, it makes this weird wave shape that doesn't actually complete itself, right? And so you can't have an orbit uh, that is like a fractional number, okay? So you're not going to have to figure out any mathematics about that on an exam, but just know though that if I give you like 4 of these things and one of them has a fraction in it, they're not probable. Does that make sense? You can't have an n that equals a fraction, okay? And that's what Schrodinger figured out. Much to popular belief, everybody thinks he came out with Schrodinger's cat, but this is actually the more important thing that he came up with. Okay, so which of the following electron orbits is not probable or improbable, right? An n equals 2, an n equals 3, an n equals 4 and 1/2, or all these are probable. Okay, I can't find this particular question, but I'll tell you now. I'll find it later when I actually have to count up all your points. I'll find it later. But the answer to this one is obviously C, the 4 and 1/2. That is improbable. That is an improbable thingy bob, right? So, wave function probability. Mathematically, the wave function represents the wave associated with the particle, which I said that a second ago, right? So for the hydrogen atom, it was found that the equation, is that an R? Yeah, R squared psi squared represents the probability that a hydrogen electron being a certain distance away from the nucleus, right? So this can represent a distance from the nucleus. So a plot of R squared and psi squared versus r for the radius for hydrogen and electron shows that the most probable radius, right, for the hydrogen for electrons from the hydrogen nucleus is 0.053 nanometers, right? And the crazy thing about that is, Schrodinger came up with this like recently, but the guy, the Bohr predicted it back in 1913. So that's pretty crazy, right? That's just some facts. You don't have to actually, know that like uh, verbatim or anything like that. But it's just interesting that we use quantum mechanics today to figure out things, and then this guy named Bohr back in the 1913 already figured it out. So he was right, right? So this is what they were talking about. This is the wave, right? This is the wave function that we were talking about. And it shows that the probability is the highest for the location of an electron around hydrogen, right? Is right around here, 0.053 nanometers, right? It's very low probability that it's out here, and it's very low probability it's at zero, which makes sense because, an electron can't get too close to the nucleus and it cannot get too far from the nucleus either, right? In the first energy level, the n equals 1 energy level, right? So it doesn't say that, but this is just like a percent over here. The y-axis is percent, okay? And so this wave function shows that the highest probability of the location of an electron away from the nucleus of hydrogen is at 0.053, right there, okay? So that's the wave function we've been talking about this whole time that Schrodinger came up with. So the concept of the electron cloud, although hydrogen's electron may be found at radii other than 0.053 nanometers, the probability is quite lower, which is what I just said on that picture, right? Therefore, when viewed from a probability standpoint, the electron cloud around the nucleus represents the probability that an electron will be at that position. And the cloud is actually a visual representation of the probability distribution. So what that means is that when you look at this cloud, notice that this cloud here is a lot darker around here, around the edge, right? And that shows that's the highest probability of where that electron is going to be around the nucleus. And as it gets closer and closer and closer to the nucleus, it gets less dark, right? It gets much more white, lighter colored. And the same thing on the other side too, right? So when people draw like electrons in around an atom, they'll draw them in this electron cloud, and most of the time they'll just make it so that it's all the same shade of color, right? But you're supposed to actually make it where it's darkest, where the location of that electron is most probable, right? So that's pretty interesting. I'm definitely an offender of this. I've drawn electrons in atoms before and just made it just a consistent, very consistent cloud, not actually reflecting the distribution, probability distribution. So that's kind of funny. So all this led to changing from the planetary model of Bohr, right, where we had like a single electron, a nucleus in the middle, and an electron floating around outside of it, kind of like a planet, right? It was brilliant, right, but it wasn't completely accurate, especially for multi-electron atoms. And so now we have Schrodinger's model, which is highly mathematical. It takes into account the wave nature, and that's what we use now to figure out where the electrons' locations are and their energies. We use the Schrodinger model, okay? So thinking way back to the very beginning of this lecture, I said, what model of the atom is most accepted today, right? It wasn't even Bohr's, right? It's actually Schrodinger's model, okay? Schrodinger's models, because I didn't even mention that guy yet back then, back like 3 days ago, or 3 lectures ago, okay? So bringing this all together, the quantum mechanical model only gives the location of electrons in the terms of probability, but this model enables scientists to determine accurately the energy of the electrons, multi-electron atoms, which is what I just said, right? And knowing the electron's energy is much more important than knowing its precise location. And then our last slide for this lecture, because we'll switch over to the next one in a minute, is this one right here, which the following is true about the quantum mechanical model, right? Quantum mechanics gives us only the location of the location of the electrons in terms of probability. This model enables scientists to accurately determine the energy of electrons, right? And knowing the electron's energy is much more important than knowing its precise location. Which of them is true? The answer for this one is that all the statements are true. Okay? All the statements are true. The quantum mechanical model does give us uh, the location in terms of probability, right? The model enables scientists to accurately determine the energy, right? And that's way more important than knowing its location. Anybody have any questions about that? All right, so chapter 13, the chemical elements. Woohoo! My favorite stuff here, okay? Finally, we get to chemistry, which we should have gotten to it like months ago, but oh well. Not my problem, right? Or I guess it is my problem since it's my class, but all right, so in chemistry, right? Chemistry is the division of the physical sciences, right, which we talked about already before, and it deals with the composition and structure of matter and the reactions by which the substances are changed into other substances. Historically, though, Egyptian, Chinese, Mesopotamians, right, they were all involved in early chemistry, right, when they were making wine, they worked metals, they did make dyes, had glass, pottery, and embalming fluids, and all this stuff happened. Wow, 3500 BC, really early on, right? Really early on. So, okay, so if alchemy was really, really big from 500 to 1600 CE, right? And mainly alchemy was all about changing common metals into gold, right? And so, or finding the elixir of life. But yeah, that's kind of crazy, right? Alchemy was concerned about changing common metals to gold and then the elixir of life, whatever that means. But modern chemistry actually began in 1774, right? 1774 with the Frenchman Antoine Lavoisier. I practiced his name in my office earlier. Lavoisier. There he goes. The Frenchman Antoine Lavoisier, right? He used quantitative methods and avoided mysticism, superstition, and secrecy. Wow, that's cool. Because back in those days, everything was like magic or something, right? And so this guy here used quantitative methods, Lavoisier, which is really cool. So there are 5 major divisions of chemistry, which we all teach here. This department teaches all of these. Okay, and those 5 are physical chemistry, analytical chemistry, organic chemistry, inorganic chemistry, and biochemistry. Right, and my specialty is actually analytical, organic, and biochemistry. Those are the 3 things that I am super good at. Right, I am those are my specialty. Right, so physical chemistry applies the theories of physics. Right, that's the reason why when we were going through atomic physics, I kept on saying how atomic physics is really chemistry. Well, what it is, it's really physical chemistry, right? So the physicists co-opted the term for some reason, who knows? Analytical chemistry, which is what I do most of the day when I'm out writing lectures for you guys, is I identify what and how much of a substance is present, right? And analytical chemistry is actually like the biggest thing that you do in forensic sciences, right? You're identifying blood, sperm, urine, trace evidence, toenails, nasty stuff like that. Bullets, cartridge cases, drugs. That's analytical chemistry. Organic chemistry is the chemistry of carbon compounds. So that's anything with carbon, including DNA, sugars, fatty acids, all that stuff, proteins. And then inorganic chemistry, non-carbon compounds. That's the one I don't do much of. I don't do much of inorganic chemistry or physical chemistry. But I got my PhD in biochemistry, which is the chemical reactions that occur in living things. Okay. So our first question for this part of the chapter is this: which of the following is not a discipline of chemistry? Analytical chemistry, organic chemistry, biochemistry, and geology. Okay, the disciplines of chemistry. 19 people have responded, and dang, someone put organic chemistry as not a chemistry? That'd be super offensive to some people in this building, by the way. Right? Super offensive. But the answer is D, geology. Definitely not a discipline of chemistry. So there are 88 naturally occurring elements, right? So those are the 88, well, most of these appear, right? Those are the 88 naturally occurring elements, okay? Either singly or chemically in combination, the 88 naturally occurring elements comprise virtually everything that we see around us, everything. So everything on that periodic, everything we see around us is made of 88 elements from the periodic table of the elements, right? The rest of the periodic table of the elements was discovered like on different planets, or sorry, not different planets, discovered from like asteroids, right, meteors, or they were man-made elements. But 88 of them are naturally occurring, right? And their chemical and physical properties affect us continually. So in this chapter, we will discuss the classification of matter, the elements, the periodic table, and the naming of compounds. Okay, so let's talk about the classification of matter. Right, we already talked about before that matter is actually either a solid, liquid, gas, or a plasma. Okay, plasma is just a gas that's superheated. Right, like you shoot electricity through it, and it gets superheated and it glows. That's the thing that we see in neon lights. Right, but anything that's made of matter has a mass, right? And chemists use this classification, but we also divide matter into several other classifications, right? We either have pure substances, they can be either elements or compounds, right? And then we have mixtures, homogeneous mixtures or heterogeneous mixtures, okay? So let's first talk about the pure substances. Pure substances, that is a type of matter in which all samples have a fixed composition and identical properties. For example, right? Elements, right? An element, for example, right? They all have atoms of the same number of protons. For example, right? If you have a piece of gold, right? It's all going to be gold atoms. That's a pure substance. Okay. You got, you're, if someone is on oxygen, right? Someone's on an oxygen tank, right? Because their post ox is super low, then everything in that cylinder is oxygen, right? Everything in that cylinder is oxygen. So all those are pure substances. You can also have compounds that are pure substances too, where it's actually made up of one or two or more elements that are chemically combined together, right, to make a new compound. But if you have all of that same compound, that's called a pure substance too. So if you buy some salt from the store, I think Gloria and her group are very familiar with salt from the store, right? That's a pure substance, right? And then, crystals or distilled water is pure substance, right? So those are all pure substances. A compound can be broken up into its separate components by only chemical processes, right? By only chemical processes. So that's different from a physical process, which we'll get to in a second. But a chemical process means that a chemical reaction had to occur to break the compound apart, right? So that's a chemical process. But then there's a physical process, like when you boil water. When you're boiling water, water is evaporating. It's just phase changing from liquid to gas, right? That's not a chemical process, and you have not broken the molecule of water in half, right? So that's the difference between a chemical process and a physical process. A chemical process will change the actual compound to something else, whereas a physical process only is basically a phase change, okay? Basically a phase change. So let's just look at some, physical properties, right? And some chemical properties for that matter, right? So here we have zinc sulfide, right? So zinc sulfide, that compound, is actually a white powder. And it's made up of zinc, the metal, right? And somebody in the lab made a zinc spoon last week. Who was that? Yeah, oh, she did. Made a spoon out of zinc. That was pretty fun. We had zinc wire and they made it into a zinc spoon. It was pretty cool. But anyway, um, it's made up of zinc and sulfur, which is interesting because zinc by itself is a silvery metal, right? That's why you can make it into a spoon. And then sulfur is a yellow powder or crystals. But you combine them together chemically and they turn into a white powder, something completely different. And then when they get combined together, right, they actually come up with completely different properties too. For example, the density of zinc sulfide is at 3.98, right? But zinc itself, the metal, is 7.14 density, and sulfur is 2.07. So you see how when you combine two things together into making a compound, it completely changes it, right? Here's another thing. The melting point of zinc sulfide is 1700 degrees Celsius. My God, that's really, really hot, right? 1700 degrees Celsius, all right? But zinc itself, by itself, melts at 281, right? And then sulfur melts at 113. So putting these guys together actually make them more stable because they don't melt as they have a much higher melting point. Here's another interesting one here. Zinc sulfide does not conduct electricity, but we all know zinc will conduct electricity, and sulfur doesn't conduct electricity as a solid. But as a liquid, though, zinc sulfide does conduct electricity, right? Zinc also conducts electricity, but sulfur still doesn't conduct electricity, right? And then uh, soluble in carbon disulfide, that's just a solvent, right? Like some liquid. And it's not soluble, but then sulfur is actually soluble. Interesting, very interesting stuff. So this is just to demonstrate to you, right, how combining two elements together will make it very, very different afterwards. So now we have mixtures. What are mixtures? Okay. Mixtures are a type of matter composed of varying portions of two or more substances that are only physically mixed together, not chemically combined. That's the difference, right? Not chemically combined, they're just mixed to each other. And so there's two types of mixtures I want you to know about. Those two mixtures are homogeneous mixtures, which look uniform throughout. That's like coffee, right? Or tea, or a metal alloy like steel. Those are all homogeneous solutions. You wouldn't think about steel being a solution, right? Because steel is like hard metal. But to make steel, you've got to melt, the components of steel, which is sometimes is like chromium and iron, and then they become a liquid, and then they mix with each other, and they become homogeneous, and then they solidify, and that's what you use to build your cars. At least cars that still had steel fenders and stuff, much stronger than fiberglass fenders. Anyway, so that's what a homogeneous mixture is, right? So technically, it should be mixed uniform at the atomic level, okay? And then we have the heterogeneous mixtures, right? Those are non-uniform mixtures, like pizza. I'm not even really sure why they put pizza in there, but pizza. But more specifically, though, things like oil and water, those are non-homogeneous, right? At least two components can be observed, right? Two components can be observed in a heterogeneous mixture. Okay. They're formed and broken down by a physical process only, which is dissolving or evaporation. Remember, I said the difference between a chemical process and a physical process? A mixture can be separated using dissolving or evaporation, which are physical processes, right? Whereas a pure substance of a compound can only be broken down by what? A chemical process, right? Broken down by a chemical process. All right. So your next question is this. Which of the following is true about mixtures? They are a type of matter composed of varying portions of two or more substances that are physically combined together, not chemically, right? Homogeneous mixtures are uniform throughout. Heterogeneous mixtures are non-uniform and have at least two components observed. And then also, not also, but all are true. All the above are true. Got 10 responses so far, and all 10 are correct so far. Got our first one wrong. Still waiting on 4 more responses. 3 more responses. 2 more responses. Or no, just 1 more. We only have 19 in here today. Right? I think so. Waiting for that last person. That's okay. So here's the distribution. One person got it wrong, like always. And then the rest of you got it right. So the answer here is indeed D. All the above are true. Okay? All the above are true. Yeah. Okay. So this is a table right here that helps you organize everything, your thoughts when it comes to matter, mixtures, and compounds, right? So we start out with matter at the top, right? And you have pure substances here, right? They have fixed compositions and properties, right? And they can either be elements or compounds, right? And chemical reactions can actually cause them to go back and forth, okay? Go back and forth with each other, okay? You can make elements out of compounds, uh, and then you can also make compounds out of elements, right? Or you can make compounds out of more compounds. So adding two compounds together will make another compound sometimes. On the other side, we have mixtures, and these are variable in composition and they in properties, right? And you have the homogeneous mixtures and the heterogeneous mixtures, of course. And to go back and forth between those two, you can have physical processes like evaporation or dissolving or something like that, right? So let's take a look at a quintessential heterogeneous mixture. This is a Italian dressing, I believe, in olive oil, some salt and some vinegar and some other stuff, right? We add it to our salad, and it tastes good, I think, right? I'm not really a big fan of Italian salads, but I'm more of a ranch type of person, but that's okay. So is ranch a homogeneous solution or is it a heterogeneous solution? Yes, absolutely, because you see those little flecks of pepper inside, right? Absolutely. What about what about? Damn, I can't think of any any homogeneous salad dressings right now. Buttermilk? No, because you can see the chunks of. No, I was about to say blue cheese, but you can see the chunks of cheese in that. Oh yeah, balsamic vinegar. That's a good one. Yeah, because it's all like brown, right? Yes, yes. Whatever the color of balsamic vinegar is. Anyway, so liquids and solutions, right? So what exactly is a solution? So a solution is literally a solvent like water, and it has something dissolved in it, right? So here we have water, 100 mils of it, right? And we add in 30 grams of salt, right? And we found out from one of our group's experiments that if you add 30 grams of salt to 100 mils of water, it won't freeze, right? It won't freeze. That's besides the point. But the interesting thing is that this is a homogeneous solution, right? Because you add the 30 grams of sodium chloride into the water and you stir it up and you don't see the sodium chloride anymore because it's completely dissolved. And so it's a homogeneous mixture, right? So there's this thing though that's called a saturated solution, okay? So now we have 40 grams of sodium chloride. We add that to the same 100 mils of water, and then you get left over 4 grams. Only 36 grams of the sodium chloride actually dissolved. We have 4 grams left over, right? And so that's called a saturated solution. A saturated solution is a solution where you've reached the point that no more salt will dissolve. Okay? No more salt will dissolve. No more salt will dissolve. So here it's 36 grams. Okay? So here are those definitions right here, right? We have aqueous solution, that is a solution in which water is the solvent, right? When dissolved and stirred, the distribution of the solute is the same throughout. That's called the homogeneous solution, like I was just talking about. We have unsaturated solution, which is a solution in which more salt or solute can be dissolved at the same temp. And then we have a saturated solution, which is the maximum amount of solute is dissolved in that solvent. So that's the saturated solution of salt water. Okay? Saturated solution of salt water. So let's talk a little bit more about saturated solutions, right? There's this thing that's called dynamic equilibrium. Okay? And what dynamic equilibrium actually is, it's the process by which when you add salt to water, right? You add salt to water, and equilibrium is when the same amount of salt is going into solution, like dissolving, as is coming out, right? And so when you reach that equilibrium point, nothing else can dissolve, right? Nothing else can dissolve. Okay, so dynamic equilibrium exists between the solute and the solute crystallizing, right? So crystallizing just means coming out of solution, right? So here we have the salt that's floating around in the water in the solution itself, right? You can't see it, and then there's the salt crystals at the bottom, right? And you can see the salt crystals getting dissolved and the salt crystals going back into the crystal, right? Becoming a solid again. And so when the rate of this guy becoming a crystal again, a salt crystal again, is the same as the rate as this guy becoming dissolved in the water, that's called dynamic equilibrium. Okay? That takes us to the term of solubility. Solubility is the amount of solute that will dissolve in a specified volume or mass of solvent, right? To produce a saturated solution. Okay? To produce a saturated solution. So we saw a second ago that it was 36 grams and 100 mils of water, right? That's basically what the solubility of salt water is, or salt is in water, right? 36 grams out of 100 grams of water, okay? So interestingly enough, though, if you raise the temperature of the water, right, the solubility actually increases. So you can get more stuff dissolved. You can get more stuff dissolved, okay? And so this is a graph that shows you that as temperature increases, right, the solubility increases as well, right? So this is absolutely apparent, right, when you're making tea, right? So sugar right here, right, sucrose, sugar right here, is generally not very soluble in water. And you know that because when you get like cold iced tea, like for example, the server at the restaurant accidentally brought you unsweet tea instead of sweet tea, right? But you're too like shy to ask them to bring you another one. So you say, let me just put some sugar in it and make it sweet myself, right? But you put in some sugar packets and it won't dissolve, right? It just sits at the bottom. So you drink your sweet tea, I mean, it's kind of sweet tea, and you get these sugar granules in your mouth, which tastes kind of good, but it's not as good as dissolved sugar in tea, right? The reason why is because sugar actually isn't very soluble in water. But then when you heat the water up and you boil it, right, you add the sugar in, goes straight into solution, right? So that's why the best time to make sweet tea and adding in the sugar is while the tea is still being brewed, right? You shouldn't add the sugar in afterwards, and you've already added the ice, right? You should always add the sugar in when the tea is still being brewed because it's still the hottest at that point, right? So this is true of most solids. This is true of most solids. The higher the temperature, the more soluble it gets, right? So here's potassium nitrate, here's sodium nitrate, right? Here's KBr. A funny story about KBr. I'll tell you about that later when we get to the more relevant thing. But KBr, potassium bromide, right? The only thing that acts weird is this mother right here, right? This guy. I think that's cesium. Is that cesium? CE. Where is CE? What is CE? You ever see CE on the periodic table? Is that cesium? I don't even know what that is. I have no idea what that is. But whatever it is, right? With the sulfate ion here, it actually acts separate differently. It acts like the opposite. The higher the temperature, the solubility goes down to like 0. That's super weird. That's super weird. Huh? Cerium? Yeah, I have no idea what the properties of cerium are. I'll tell you right now that the vast majority of chemists ignored this bottom part right here. This is called the lanthanide and actinide series, right? There's a reason why it's not a part of the periodic table. It's not because it went out of room. It's because nobody cares about those guys. So nobody cares about them. Okay, I take that back. Some people care about those guys, but the vast majority of people care about the ones that deal with life, which is the ones up here, right? So cerium, for some reason, cerium sulfate here acts differently than the rest of these guys, right? Cerium sulfate, don't worry about that little guy, okay? If I ask you a question about the trends of heating up liquids and how it affects solubility, what's going to happen? It's going to increase solubility, okay? Don't worry about the one guy down here that does the exact opposite, okay? So, okay, supersaturated solutions. Oh, boy, do I have a story about supersaturated solutions. When an unsaturated solution are prepped at high temperatures and then cooled, the saturation point can be reached as the solution cools. So what happens is that you can add in a whole bunch of stuff extra and make it more soluble because you have it at a higher temperature, and then you let it cool down, and then you have what we call a supersaturated solution, right? Here's a solution of sodium acetate right here. It's in this little petri dish. This literally looks just like what the freaking heating pads look like, okay? except they had colors in it, so they enticed you with pretty colors, right? And then all you have to do is drop a piece of metal in it, and it starts to crystallize, right? And it makes this like cool looking crystal that goes throughout all the plastic bag. But when this happens, a whole bunch of heat is released, and it releases for a really long time. So so this is what happens when you have a supersaturated solution, right? And you let it cool down and it's clear, right? And then you drop in a piece of metal. It could be anything. You don't have to be a piece of metal. It could be anything. And all it really needs is what they call a nucleation site, right? So it's the same reason why when you have Coca-Cola bottles and you take like a Mentos, when you throw it into the Coca-Cola bottle and then it explodes, it's the same thing, right? Those Mentos have little pores on them that are called nucleation sites that cause bubbles, right? Imperfections, and then that's what makes the Coke just fly everywhere, right? Same thing here. You drop anything in there, causes a nucleation site. So instead of causing bubbles, it actually makes it where there's places for crystals to form, right? And here the crystals form and they get super hot, and people use it for heating pads that they can make at home, but then they spend $80 on each one of them. Anyway, I'm a little bit salty about that. Ha, get it? Salty? Salty, get it? A little bit salty? Yeah, funny, right? Oh, oh, okay, whatever. I'm gonna remember you guys didn't laugh at that joke. Okay, I'm gonna remember that. All right, next question. A solution. Oh yeah, you did. I'll remember that. You did laugh. It's hard to tell with masks on. So maybe you all laughed and I just couldn't tell because your masks are on. Except for Matthew back there, didn't have his mask on. I saw him not laugh. So I'll remember that he didn't laugh at that joke. So a solution that contains more than the normal amount of dissolved solute at a given temperature, more than the normal, right, maximum amount, is known as a what? An unsaturated solution, a saturated solution, a supersaturated solution, or an aqueous solution. I just spent 10 minutes talking about saturated, supersaturated solutions, so you better get this right. You talking about the restroom? It's on the other side of the stairwell. All right, let's see how you guys did on that question. I got 13 responses so far. Still waiting for. Oh, we have 20 now because Sydney showed up. It's okay. I'm not worried about it. You can watch all my crazy stories on the video. All right. I don't know how this happened, but all four answers were actually picked for some reason. But at least the one that was correct is the one that's picked most often, which is C, right? It's a supersaturated solution. So when you get a question on the exam that talks about heating pads from this company called, oh, what is it called? Dang, I'll remember it later. From some company, some obscure company that get hot when you click a piece of metal inside. Remember that it's a supersaturated solution. Okay, I'll probably on the exam just have a picture of it, and you have to be like, what is this? You know. So things for my life is what it is that caused me angst. Okay. So another interesting thing here is that the solubility of gases is actually the opposite, right? So um, So when you heat up a liquid, it makes solids more soluble in that liquid. But it's the opposite with a gas. Okay? Gases are more soluble in liquids when they're colder. Okay? And this is the reason why if you leave a Coke sitting out for too long, right, it gets flat. And the reason why is because it gets hot and all the gases, like the CO2, that doesn't kill you, by the way, it's not harmful to you, okay, because you drink it and you're freaking. I should have said that. She even had a Dr. Pepper can next to her. Dang it. Dang it. You're probably right about that. Dang it. I should have thought about that, though. Anyway, so your can of Dr. Pepper, if you let it sit out for too long in the sun, the heat sun of Texas, hot sun of Texas, right? The Dr. Pepper can will get hotter, and that actually makes all the CO2 that's dissolved in it, that makes all the fizz go away. It actually just floats up into the atmosphere, okay? And that's why your sodas go flat. So if you want your sodas to stay stay carbonated, right? Increasingly fizzy, just keep them cold, right? Keep them cold. And they'll do that. So there's this guy named Robert Boyle, right? In 1661, he proposed that the designation of element can only be applied to substances that could not be separated into its component by any method, right? So what that means is that elements are the smallest component of any piece of matter, right? You can't go any smaller than an element. Does that make sense? Okay. In addition, Boyle initiated this practice of carefully and completely describing experiments so that anyone might repeat them and confirm them, right? So that's actually the basis of all science today, where we write. I don't make you guys do this in lab, right? But usually in a lab, like especially the Majors lab, they've got to write down every single thing they do in a notebook, right? So that somebody can come in after them and do the experiment again to make sure they did it right, right? And so that's it's a process that we call like peer review, right? And it ensures that experiments are being done correctly, right? And it's especially helpful in drug discovery and stuff like that. Well, you wonder why drugs take so long to discover. It's because we go through all these processes, right, that take forever. For example, peer review and writing down all these steps and all that stuff, right, and testing it over and over and over again, right? And that's why the normal drug discovery timeline is like 10 years, right? 10 years. And that includes all three phases of drug discovery. Okay. So let's talk about the discovery of the elements, right? The earliest civilizations isolated 12 substances. They isolated gold, silver, lead, copper, tin, iron, carbon, sulfur, antimony, arsenic, bismuth, and mercury. And all 12 proved to be elements. The earliest civilizations, right? I mean, we're talking like in the BCs, right? That's crazy. I can't isolate anything now. And we're in the 2120s, like 2021s, whatever. Another interesting note here is that phosphorus, right? P up there on the periodic table, phosphorus, right, was isolated and discovered from P in 1969, right? So in 1746, platinum, cobalt, and zinc had been discovered, and then by the 1800s, 10 more elements were added, right? Crazy, crazy, crazy. How fast chemistry happens, right? And then around 1880, Davy, I think his name is Jeffrey Davy, an English chemist, used electricity invented from the recently invented battery to break down. The battery was invented before 1880. That's crazy. Recently invented a battery to break down compounds, right? Thereby isolating 6 additional elements: sodium, potassium, magnesium, calcium, barium, and strontium, I believe. Yes, yes. So those are all metals. That makes sense. It took electricity, right? It took electricity to isolate those guys because those are all metals, right? And so by 1895, 75 elements were known. I mean, before the 1900s, we had 75 elements already on the periodic table. That's crazy stuff. During the next 3 years, noble gases, helium, neon, krypton, and xenon were discovered, right? If you're like a gamer, right, you know a lot about xenon because Intel makes a processor called the Xenon processor. It's supposed to be super fast. Pales in comparison to like the M1 Apple chip, though, by the way. So, sorry, I have a background in computer science too. Anyway, so in addition to the naturally occurring elements, 30 synthetic elements have now been created. So a synthetic element is literally an element that is man-made, okay? Element that's man-made. 30 of them. 30 of them, okay? And so this is a cool little chart that shows how the trajectory of chemistry, right? It's so neat, right? If you saw a chart like this of physics, it's like a flat line, okay? Literally. Or geology, it's like a flat line, right? When you see a chart like this for chemistry, and you can see how elements just get discovered over and over and over again. Here's Boyle, he discovered 12 elements. Lavoisier, the French guy, 22 elements, okay? Davy, oh no, it's not Jeffrey Davy, maybe it's Humphrey Davy, whatever his name is. Mendeleev, the Russian guy, he actually created the periodic table of elements just by figuring out the weights of each element, like literally weighing them. And somehow back here in the 1800s, 1850s, somewhere between there and there, he discovered 63 elements, and then he still left spaces in between the periodic table for the unknown elements yet. Then we got Marie Curie, right? Marie Curie here, she discovered 82 elements. Some of them were radioactive, like radon. So I don't know if you remember back in the day, there were these ladies that were making watches. They had like glow in the dark faces, right? And the way those watches had glow in the dark faces is because they took radon, which is a glow in the dark pigment, right? And they would paint on the numbers onto these watches, okay? But which is really bad though, because what they do is they'd lick their paintbrushes to make the paintbrushes very thin, right? And then they do that and lick it again. And, instead of using water, a cup of water, they'd lick it, right? But no one knew at the time that radon was actually super radiation, right? Very radioactive. So all these ladies ended up dying from the radon factory of radiation poisoning. That's crazy, right? Yeah, it's crazy stuff. Crazy stuff. I'm just I'm just a vessel of useless knowledge. Yes. Okay. The last slide for today. Which of the following elements was discovered by isolating it from pee? I swear, if any of you get this one wrong, if any of you get this one wrong. Isn't chemistry so much more interesting than the other sciences? I think it's super interesting. Did you just shake your head, Sydney? I'm so sad. It's because you came in halfway through. You didn't see the intro, right? Yeah, I'm trying. I'm definitely trying. Okay, this one is called P, I believe. All right, most of you have submitted, and the vast majority of you gotten that one correct. The answer is indeed phosphorus. Again, if you don't forget P, golden showers, phosphorus is all. It all starts with P, except for golden showers starts with an S. But whatever, G and S. But just remember phosphorus from urine. And then that ends today's lecture. Put your desk back together, and I will see you guys on Wednesday